All right, so to pick it up from the last section, I'm going to go a little quicker over this. So we're going to jump into levers. I want you to understand that there's 3 different types of levers. So that's why there's 3 images here. They're broken up into classes. So we're going to say first class, second class, third class. And what differentiates it is the location of effort and force in each one in relationship to the fulcrum. So we'll go through some of those specific terms. So the first type we're going to look at is first class levers. The 3 images below are all first class levers. They're like a subcategory of them. So what they have in common is the fulcrum is located in the center, not necessarily in the center, but somewhere in between the effort and resistance forces. So in each situation, you're going to see that the effort and resistance forces are on either side of the fulcrum. The big thing is, if you have a mechanical advantage of 1, that means they're equally distant from each other, so it is directly in the center. If the mechanical advantage is less than 1, it means that your distance between the effort is shorter than the resistance distance. It also means that you're going to have to put a greater effort, which is why the arrow is larger. Greater than 1 means you're putting a smaller effort, that's why my arrow is smaller. But I'm also a lot further away from the fulcrum. Okay. So second class levers. So fulcrum is located on the end. Big thing to note, so it's on the end of one side. The resistance is in the center, or closer to the fulcrum, and the effort's on the outside, but they're still on one side. That's the big thing I want you to note. So they're both on the same side of the tipping point, so the forces are on one side. But the resistance is closer to the fulcrum. Second class lever, the big thing to note is it always has a mechanical advantage greater than 1. And that's also always because the effort is always farther than the resistance from the fulcrum, which means greater distance, less effort. Third is the opposite, where the effort is closer to the fulcrum than the resistance, so it always has a mechanical advantage less than 1. Big thing to note. When it comes to moments, you know, some of the things that I want to make sure that you guys pay attention to is the fact that moments is equal to distance times force, but it's a perpendicular distance, which, we'll go into a little more detail. Also, I want to make sure that you guys understand that these 2 words are synonymous with each other. Really, for me, the only difference is moment is when I don't want it to turn, so it's more specific to statics, where everything is in place, whereas torque is related to dynamics, or where you're okay if things spin. You want them to move, but those are synonymous. We'll go over an example of moments. So if I want to calculate the effort moment, and if I'm using the formula again, moment equals distance times force, where the distance is the perpendicular distance, then my distance from the fulcrum, okay, so if I were to draw this right here, well, notice that the distance from the force is 5.5. The force itself is 15 pounds. So in order to calculate that, moment equals distance times 4, I'm going to get an effort moment of 82.5 inch-pounds. Notice the units. You do want to pay attention to the fact that we have a distance and a unit of force. That's going to be different if we're talking about something like SI units, which is going to be something like, blanking out right now, what is it? Newton's meters. That's in SI units. International units. Just to give more kind of background in terms of what moment means, it's your desire to want to rotate about a fulcrum. So maybe this won't mean much now, but the fact that it says 82.5 pounds inch, that's giving me some indication of how much it wants to turn, how likely it is that it's going to spin. We can do the same calculation with the moments of the resistance. I'll move through this a little faster. But when the moments of the effort and the moment of the resistance are equal, that's when we reach rotational equilibrium, which means that if your desire to spin in this direction is the same as the opposite desire to spin in the other direction, then you're not going to move at all. You're going to stay in place. But if I have a situation where I have a lever and this one is a lot bigger than the desire to spin around that side, then it's going to go ahead and make sure to spin in this direction. You're not in rotational equilibrium unless it's completely unless the moments are equal, or the sum of the moments are completely equal, and there's no ability for it to turn because it's staying in place. Why? Because these two sides are equal. So if I wanted to do that calculation, if I wanted to know, hey, I can put this amount of force, but I don't know what kind of distance I have to travel to keep this beam to not rotate, I can use this calculation where, you know, effort moment is equal to effort resistance moment. So force times distance is equal to force times distance. If I look at mechanical advantage, ideal mechanical advantage, you know, I'm not going to spend too much time here, but just realize that for levers, you're going to use the same formula we've already written. It kind of goes through why. For a actual mechanical advantage, we're going to use the same formula as well. AMA is equal to FR over FE. That's going to always apply for all our simple machines. So in this example, what's the mechanical advantage of the lever? Well, my resistance, again, so force of resistance is equal to the 32 pounds divided by my effort of my force of effort, which is 16 pounds, which means I'm going to end up with the mechanical advantage of 2 to 1, which means, again, I need to go ahead and put less effort, but it's going to be a greater distance away. The mechanical advantage now, what type of lever is it? Well, or what is the IMA of the lever above? Well, that means I'm going to look at the distances of the lever. So the effort is a farther distance than the resistance is. So the effort's going to be bigger than the resistance. So if I plug and chug, I see that the IMA is greater than the AMA. So why is that? Well, that's because of something called friction and frictional losses. No system is 100% efficient. If it was, then that would mean that you've created an ideal machine. It means that there's no such thing as you're in a perfectly frictionless environment and no energy is wasted from movement on anything. So it's a perfect system. It's a perfect machine. That's kind of the kind of concept that if I if I were to roll a ball down on the floor, it'd always roll because friction would never stop. There'd be no wind resistance, anything like that, which is crazy to think of. It's not really possible. Machines try to get as close to 100% efficiency, but they're so far away from it, especially motors. We lose a lot of energy in just frictional forces. But we can plug and chug to see what kind of efficiency we have. In this situation, in the previous example, that meant we had an efficiency of 82%, which means there's 18% efficiency loss from things like friction and stuff like that. Again, no system is 100% efficient. If it was, you've created essentially an ideal creation, an ideal machine. Not possible. Wheel and axles are going to be very similar to levers, but let's think of a couple examples. Here we see a steering wheel, a knob, another knob. They're going to follow the same formulas. I'm not going to explain too much on that, but in this situation, if the axle is driving the wheel, which means, again, I'm placing my effort on the axle. So this would be the axle right here. Axle. If I'm placing my effort on the axle, then that means that the axle is driving the wheel. This is like a bicycle. When you rotate, it's the axle that makes the outside wheel move, not the other way around. Not like a steering wheel. On a bicycle, you're not grabbing the outside of the wheel and then making it spin to make the axle move. It's the opposite. It's the axle that's making the outside wheel spin. So if that was the case, the ideal mechanical advantage would be 3 to 10. Okay? But if it was the other way around, where it's just like a steering wheel and I'm putting my efforts on the outside and it's driving the inside axle, or something like a handle on a sink or something like that, then it's the opposite. Then it's 3.33 to 1. So these are kind of opposites. That's the point. Same with the actual mechanical advantage. We'll note that it took 200 pounds of force what would this be, resistance. We put 70 pounds of force on the outside, so this is a situation where the wheel's driving the axle. Yeah, so the wheel's driving the axle. So what's the efficiency? Well, plug and chug, 85.9. Pulleys, quickly, there's two types. Actually, there's multiple types, but fixed pulley, multiple pulleys. Movable pulleys always have an ideal mechanical advantage of 2. Fixed pulleys always have a mechanical advantage of 1. Then there's something called a block and tackle. This we count the number of strands. So in this situation, the strands opposing the force of the load. So as this moves down, these actually conceptually move up. That's why it's going to get shorter. This whole object is going to move up. Think about it. So that means these strings are actually getting smaller and smaller. These ropes aren't actually extending. Instead, as I pull down this rope, these ropes are getting shorter and shorter, so that by the end of it, it might look something like this, where these are all in a pulley system. It's smaller than what it started off as. So the number of strands opposing the force load is 1, 2, 3, 4. So the mechanical advantage of this system is 4. Compound machines are when you have a combination of pulleys, levers, or any kind of simple machines. In order to calculate the mechanical advantage, you multiply the ideal mechanical advantage of each of the situations. Pulleys in combination essentially act the same way. You multiply them to get an overall ideal mechanical advantage. And with actual mechanical advantage of the system, even though I'm pulling up 800 pounds by putting 230 pounds of effort down, that means that, again, my resistance was 800, my effort was 230. So my actual mechanical advantage is 3.48 to 1. If I compare that to the efficiency of this pulley, well, 1, 2, 3, 4 strands, that would mean that the ideal mechanical advantage is 4 to 1. So compare the two, 87%. Common misconception, really, in the previous example, unless it's directly straight up and down, vertical, you don't really have an ideal mechanical advantage of 2. In reality, you have some kind of ratio of 2. The bigger the angle, the smaller. But for this class, we're gonna just assume that the ropes are completely vertical. Okay. That's about it. So I know it's a long video, but hopefully it helped.